Yes, I'm with Juniper. It's another vendor without a hospitality room at this network. And the topic to cover today is SONET. I understand a lot of people have been using SONET for a long time. They're very comfortable with it. This talk is not for you. Do whatever you do after a long lunch and at the beginning of a half-hour talk. This is for the other people whose backbones are at the DS3 level now, growing towards SONET speeds and feeds, and want to understand the technology. It also sets up some of the subsequent talks on next generation technologies coming up after me. I apologize that these slides are not yet posted online. They will be in the next day or two, perhaps even a slightly enhanced and corrected version of those slides as well. So it'll be worth downloading the new ones, even if you choose to take notes. Understanding SONET requires entering the Wayback Machine, all the way back to 1984. This was the state of networking, digital networking at the time. Digital telephony had been around for a decade or more prior to this. But the system grew up around proprietary, well, not proprietary, but specialized devices, DS1 multiplexers bringing in individual phone circuits up to the 45 megabit level that we're accustomed to with DS3 circuits. There were some proprietary fiber optic transmission systems, multiplexers, but they were pretty much the bane of the single dominant network vendor of the time, AT&T, and their single dominant equipment vendor of the time, Western Electric. So you had the capability to get digital circuits end-to-end T1 DS3, but no standard way of doing it. And that was pretty bad, because in 1984 something big happened, divestiture in the States. Judge Green broke up the Bell system. Suddenly, it was no longer assumed, it was no longer a reasonable assumption, that the equipment at either ends of a link might be run by the same entity or even manufactured by the same vendor. And that assumption broke big time. The way the new emerging telephone entities expressed the requirement that devices should be interoperable is with the single phrase mid-span meet. They wanted to put vendor X here, vendor Y there, light up the fiber in both directions, and have the devices talk to each other. This was critical. Standardizing common maintenance procedures, supporting various topologies, all would fall out of the ability to interoperate with different vendors. An additional side benefit of this new approach would be to enable cross-connecting that was much more graceful than was possible with the previous configuration. Here, DS1 level cross-connects had to be done by demultiplexing the DS3 because of the bit interleaving. And they wanted to get away from that. They wanted to be able to get down to the DS1 cross-connect level without a 7-foot rack of equipment or 2 7-foot racks of equipment. Now, the standard to get there, to get to mid-span meet, almost didn't happen. In the States, the process ran fairly smoothly, and people understood the need. And so starting in '84, and actually a little before, people have been talking about SONET and working to get some generic requirements, to get some rough idea for what it would and should be. Somewhere around the middle of this timeline, the international folks noticed this was going on and thought, even though divestiture wasn't happening in their environments yet, it would be wonderful if the world was moving toward a single standard. So there started to be cross-pollinization in early '87. The British and Japanese delegates started participating in the ANSI committee. And towards the end here, it seemed for a minute that the needs of the two communities wouldn't be fused. Finally, there were some last-minute compromises, and in the span of only 4 years, actually it's pretty good considering who we're dealing with, both a domestic version, a US version, and an international version that were inherently compatible, at least at the bulk of the levels, were finally adopted as standards. Since then, there have been a couple additions, phases, and modifications to it, but basically that's End of 88 was when the official stamp was there. The standard, the Synchronous Optical Network, is a layer 1 standard. It's to facilitate the communication over fiber optic links, to provide mid-span meet, inter-vendor compatibility, and also with an eye towards handling increasing fiber optic speeds, as well as adding functionality, adding the ability to groom circuits. For the telephone company, getting down to the DS1 and DS0 level was key to their business. So manipulating bandwidth at a finer grain without large amounts of equipment was critical. Common operations administration procedures were vital as well. As everyone knows from running an IP backbone, if you can't manage it, it doesn't do you much good. So the standard provides all of this. Before talking about the protocol formats, it's useful to talk about the kinds of equipment that the vendors would need to handle the SONET frames, and break them down into three rough categories. The section termination devices include things like repeaters that do electro-optical conversion. They take in the light pulses, convert it to an electrical signal, resend the electrical signal on another optical transmitter, and do some cleanup, basically looking for timing and reconstituting the timing streams, as well as providing a stronger light signal, even though we can do that with other technologies as well. The line termination devices are things such as add-drop multiplexers, which we'll talk about more in a little bit. They're more higher up the OSI stack in a way, even though everything's still at layer 1. They do more processing of the information, but they don't terminate or originate information sources. Certainly, repeaters don't either. They pass it through. They're fairly unintelligent devices. These have to be more intelligent to process information and to get it to the direction that it's going. But still, they're not a source for DS3 information or higher speeds. They just pass it through. The path termination devices originate or sync the information. They're the ones starting the communication or ending the communication. As it turns out, the SONET frame format has overheads associated with each type. And knowing that those three types exist is critical to understanding the frame format. Here's the beautiful drawing layout, the common SPS1 frame format, and I'll talk about what that means in a little bit. It's 90 bytes wide. Obviously, PowerPoint can't quite accommodate that, so what is actually a byte looks like a vertical rectangle, pardon the aspect ratio. The frame is laid out as 90 bytes across by 9 rows high. Each byte, 8 bits, transmitted most significant bit first, starting with this byte running across the top row and then going back that way. The entire frame takes 125 microseconds to send. It should be familiar. That's the equivalent of the time, the intersend interval for every byte in a DS0, or one voice sample interval. And this was created by a telephone company, so they wanted DS0s to map nicely to SONET frames, and they do. As a result, choosing this frame structure with 810 bytes per frame gives an aggregate data rate that's after the overhead of 51.84 megabits per second. And because some of the overhead isn't available for payload, the actual capacity of this is just around 49 megabits per second. And that's enough to accommodate a DS3, which is in part why this frame format was selected. Each frame, by the way, handles just a single payload. So it's not that you're going to put in a DS3 and a few extra DS1s to fill in the excess capacity. It's a DS3 and that's all you get. Now the section overhead bytes, remember they were up in the very top part. The first byte to be sent was actually a section overhead byte. The first 3 bytes to be sent in the frame were section overhead. These, again, diagrammatically, these are originated and sunk by every section termination device. So here you have a repeater, you have an add-drop multiplexer, which we'll talk about, and the overhead bytes at the section layer are added at this device, removed at this device, and the new ones are added as information flows through. So this, the section overhead is terminated at each device, at every STE. The meaning of the bytes of the 9-1 is pretty straightforward. The first two are sync bytes. They're what help the devices find the beginning of the frame throughout the transmission at every device. The second one was intended as an identifier for a particular SDS frame or originating device. It's not widely used. The bitbait is a bit interleaved parity, which is applied to all the bytes in the section overhead to help protect against bit corruption. E1 is an order wire. The purpose of the order wire was so that a technician could plug in a telephone into this device and talk with another technician who plugged the telephone into that device. So it was assumed each STE would build in a very simple codec for a telephone, for a single handset, and that even if the rest of the communications were down, two technicians could work together to troubleshoot a problem through that mechanism. It's not widely used. The F1 byte is a user-defined byte, so a vendor could still implement a proprietary management mechanism between SDs if they choose, but the way they're intended to manage these devices is using the 3 bytes, D1 through D3, which are added together for 192 kilobit per second datacom channel. And on top of that, the device is supposed to run a full OSI stack and be CMIP manageable. And we'll talk a little more about that in a bit. The line overhead, again, this is between section terminating devices, the devices that are smarter than the STEs, is also originated by STEs and terminated by STEs. It is not, I'm sorry, by LTEs. It's originated by line termination equipment and sunk by line termination equipment. It's not, in fact, touched as it passes through the section devices. Again, it's got a fairly simple 18 bytes of overhead. We're going to talk about a lot of them in a little bit. The key ones to note now are that 9 bytes constitute the data communication channel for about 576 kilobits of OSI manageability. And the 2 key ones are the H1 and H2. These are pointers to the beginning of the path overhead. One of the fundamental goals for SONET was to accommodate plesiosynchronous clock sources, devices managed by other phone companies whose reference may not be precisely tied to their own clock source. This requires back in those days, in order to build equipment that supported that, they didn't want a lot of memory or buffer memory in the devices. So they allowed the payload to float within the frames, and in fact, the path payload floats across frames because the 2 line overhead bytes, H1 and H2, point to the offset where the path overhead begins. The path overhead, because it begins sometime after the line overhead section, almost always spills into multiple frames. This ability to spill over and then to adjust the pointer to affect where in the spill, how much you spill over and whether you back it up a little bit, is what gives SONET its ability to adjust to different clock sources from the devices. The actual data payload trails the beginning of the path overhead. It starts streaming in bytes after the start of the path overhead. This is the path overhead. It wraps around frame, and then the data bytes are wrapped around left to right in the subsequent bytes. A little better explanation of how the jitter is accommodated. When the payload requires some slip, some positive stuffing, in other words, you're late delivering enough bytes for the payload, there's a complicated sequence that happens with H1 and H2 that indicate there is a slip coming up. You cannot slip every frame and you cannot adjust the payload by more than one. In fact, you have to wait 4 frames to adjust the payload. But when you see this slip is coming, H1 and H2 take on special values. If it's a positive slip because data is late in arriving, you add an extra byte after H3, after the third byte of the payload. This is what the receiver ignores in order to delay the beginning of the next data envelope beginning. So you can see how everything shifted as a decision was made to stuff an extra byte and move the payload one more. You could not have another shift until 4 more frames. You can also accommodate negative stuffing if data is coming in slightly too fast for you to accommodate, and you need a little extra space in the payload envelope. H3 takes on the value of user data that's just put in sequentially with the normal scan. So you get an extra byte of payload, and then the next frame begins 1 byte earlier. Now, for this very useful but low resolution stuffing mechanism, you have to have some general synchronization among the clock sources of all the devices in the SONET network. And this is accomplished by a clock distribution network that runs in parallel to SONET. That's what the synchronous implies. There is a common master clock to which everything is slaved. Ordinarily, the way this is usually implemented in the central office is the building integrated timing supply is a device which feeds the different SONET devices, usually by a separate wire, but it's also possible for devices to recover timing from the line, just like modems recover timing from the other side. The bits clocks are all traceable to a stratum 1 reference, which is accurate to 10 to the minus 11th. And under normal conditions, everything is synchronized to that level of accuracy. So the rate at which slips occur is very, very low. Several years when everything is synchronized. When a device loses the source of timing, it's usually able to either fall back to a backup reference, or if it needs to run internally, it may have a lower resolution reference. It allows it to run for a little while. The error rate will go up, but when the network is repaired, everything will be fine again. Now, all this bit clocking would not be very worthwhile if SONET could only go up to 51 megabits per second. In fact, it goes up much higher. We saw the format of the STS-1 frame. In general, SONET STS-N frames refer to a strict byte interleaving of a number of STS-1s. You basically take a large number of frames from all individual separate STS-1s. You take the first byte from the first frame, second byte from the second, third from the third, so on, and then wrap around until you get to the second byte of the first. In this way, SONET defines STS-N circuits for many values of n. I haven't written them all here, but these are the most common ones. And as you can see, at STS-3, STS-12, STS-48, you're already considerably exceeding the capacity of a single DS3. Now, this version of combining SONET feeds still creates and handles individual STS-1s. Each one is its own separate STS-1 and only able to accommodate up to that 49 megabit per second payload. The STS-NC format, where n can be any of the same values as it was in the previous slide, refers to a concatenated version, where instead of adding together a large number of STS-1s, you have a single large payload contained in this faster data rate. Now, in order to keep the circuitry simple, there are still the same number of overhead bytes in the transport overhead section. That is, if you have an STS-3C, you still have 3 overhead bytes, 3 times 3 overhead bytes, or rather 9 overhead bytes across in the purple section for a total of 27. But because it's in concatenated mode, you only pay attention to some of those. It doesn't make sense to pay attention to all of the overhead bytes anymore. The parity, for example, is useful because it protects, each parity byte is going to protect a different interleaved byte in the payload. But, for example, the data communications channel, you don't need n data communications channels in this case. So you only pay attention to the first DCC byte in the overhead. With the greater speed of SPS-NC, you can accommodate FDDI and the European E4, which is around 139 megabits per second, and part of the whole motivation for the compromise that was reached on SONET. All we've talked about are the encoding of bit rates and an electrical waveform, or maybe just a virtual waveform. Before this is actually transmitted, it's passed through a scrambler of only 7 bits in length. Not all the bits are scrambled as it's sent out the optical link, and there are several optical standards defined for use with SONET. So you can have long reach, intermediate reach, and short reach SONET links, and you'll pay only as much for the optics as you intend to pay. There's also an electrical transmission standard for the lower bit rates of SONET, and that's useful for intra-pop applications. Now, with these higher speed interfaces, there are several network elements defined. Some of these names are standard, and some of them are industry jargon, which varies. In practice, you may buy a single device from a SONET vendor and operate that device in any one of these modes. So it doesn't necessarily imply a whole product portfolio exists for each one. It may be a single device. The terminal multiplexers have a single OCN interface to the network, and they accommodate a certain number of lower speed channels coming in. There's no routing of information through the DS1, through the terminal multiplexer, other than between the low speed interfaces and the high speed interfaces. With the add-drop mux, that's not necessarily true. It's got the ability to have inputs and outputs passing through it, and to be able to take data coming in from the left, take it off the ring, or take it off the line, send it down to a DS1, take other data coming in other DS1s and send it out back to the terminal multiplexer. So it acts as a sort of a revolving door with multiple exits as traffic comes in the various interfaces and gets shot back out. The matched node provides some redundancy. Again, usually a function built into the add-drop mux itself. The digital cross-connect is what provides the phone company's ability to map circuits down at the DS1 or in some cases DS3 or OCN level. In the generic sense, the wideband digital cross-connect allows the low and high speeds to be cross-connected internally, whereas the broadband is typically more towards just OC3 and up, or OCN and up. With these network elements, these building blocks, SONET topologies are somewhat standardized. A lot of carriers put them together in typical configurations. One aspect of that is the number of fiber rings that you use. A 2-fiber ring implies a full duplex connection between every adjoining ADM, arranged topologically in a circle. In a 4-fiber ring, you've got a pair of active and protect fibers running around from each one. I'll say more in a little bit. There's also the ability to classify the topologies based on the directionality of the traffic. So let's take, for example, a 2-fiber ring. A unidirectional ring routes all traffic clockwise by convention. So traffic coming into this ADM goes the long way around the circle, even if it's going out to its neighbor. And traffic, oops, that arrow should be the other way. Traffic coming in here goes the short way to its neighbor. It provides asymmetric delays. So if you're on a large ring and you're pinging between routers on both sides of those ADMs, you will actually notice pings taking, I'm sorry, if you had a tool to measure unidirectional delay, not ping, you would actually notice a difference. With the bidirectional ring, traffic can take the shortest route to its destination. Every one of these network elements is supposed to implement a full OSI stack for manageability. It uses that to communicate with other nodes over the data communication links built in. And of course, it has hardware level detection to tell what's happening to the lines and to the circuits based on those overhead bytes. And these happen too fast to process in software, so this is built into the SONET level hardware. These hardware detection events are not only passed up to the OSI level for communication with other devices, but they also trigger other hardware error signaling results, so that when a given node sees a problem with a line, it can very quickly at the hardware level signal an adjacent node that something's wrong. And using this, SONET provides an automatic protection facility. This is hardware level detection of problems on lines, including bit error rates and loss of signals, loss of frame, and in some cases taking an appropriate restoration action, which can happen usually in the time frame of 50 milliseconds. There are two general types with line protection switching. There's spare backup capacity. It's idle all the time, and only when a path is detected to have a problem is traffic switched to the other line. With path protection switching, the path overhead bytes are used, and the traffic is duplicated over both primary and protect circuits. In the event of a failover, the protect just picks up. This allows more flexible restoration, and a lot of people are moving towards this, but this has a slight advantage if cost is an issue, because you can, with line protection switching, use a single protect circuit to back up several lines. Brief word about packet over SONET. There is an update to RFC 1619. I don't know if it's been assigned a number yet, but it has specifies all the conventions for making an HDLC EPP payload in an STS1. It basically used all the standard encapsulation with some recommendations for options. Except for OC3, all packet over SONET is supposed to use the 32-bit CRC. There is a scrambling polynomial with the x to the 43 that protects against spoofers from sending long payloads and guessing that after the SONET level scrambling, after the optical level scrambling, they could specify a pattern that might have too few zeros for the remote side to synchronize, or might also spoof the sync bytes themselves. So this was added after people realized there was a potential denial of service attack there. How does this relate to other things? Well, the synchronous digital hierarchy is the European version of SONET. It is, for the most part, compatible. You don't have to redesign chips completely to work for one or the other, but there are some differences in how the overhead bytes are handled, as well as the terms. The SDH standard starts at what we call SDS3, and in fact, they call an SDS1 for what we call an SDS3. So when you start seeing STM in the context of SDH, just multiply their number by 3, and that's the equivalent SONET or OC hierarchy bandwidth. There are also some simplified data link proposals on the table that fix some of the problems of HDLC for use over very high speed links at these SONET rates. So you can reuse the same optics, the lasers and receivers, but not incur some of the SONET overhead processing. Let routers do it at layer 3. And some of those are in theory, you recover some of the SONET overhead that you would otherwise paid, which of course still isn't as bad as APM. Finally, and I think this is coming up in the next talk, the wavelength division and dense wavelength division multiplexers that are on the market today may, or will be coming to the market, may in fact provide some of the restoration capabilities that SONET's so useful and liked for. So it will be interesting to see how the two find the niches in the market. It seems unlikely that SONET will be thrown overboard by the telco vendors anytime soon. It still provides access to the lower layer signals. It was one of the motivating reasons for developing SONET to begin with, and it really doesn't have a comparable function at the wavelength level, where you still have to demodulate an optical signal and then electrically demultiplex it to get at the lower bit rate. So maybe there will be some peaceful coexistence. When this is posted, you'll have a brief list of acronyms and references from which some of this information was pulled, and we're going to try to keep you on time. So, thank you, and we'll keep moving.
We maybe have time for one quick question. If I see someone moving, no, they're walking away. Okay. Any questions?